Welcome to Ready to Derive. In this video, we will be exploring graphical connections between a function and its first and second derivatives. In particular, being able to look at a graph of only the first derivative and infer features of the original function. But the three are interconnected, so it's important that we examine them all together. I will be drawing on material I covered in this video, the first derivative in the shapes of curves, which you can go and check out if you need a refresher, and the second derivative in the shapes of curves. But I will actually be reviewing the key takeaways from these videos in the opening slides of this presentation. So no need to go back to the videos themselves unless there's still some questions unanswered. So without further ado, let's get started. So let's just recap graphing derivatives of a function. So this is the function f, and we're going to graph f prime and f double prime. Just make sort of rough sketches. So recall that f prime represents the slope of f at any x value. And it's always good to go in sort of constructing f prime to look for horizontal tangent lines on f. So there's a horizontal tangent line, which means the slope is 0 there. So I can record this value on f prime, and we have another horizontal tangent line. So f prime must have an x-intercept there. Then we'll take some sample points. Let's take the slope at x equals -3. It's pretty steep. I'm going to say it's about 6. Could be anything, 6 or 7, but let's say it's about 6. And at -2, maybe the slope is around 2. And we can see that we can begin to connect the points. Now what happens after x equals -1? The slopes of the tangent lines are negative. They get pretty steep negative there, and then they pan back down to 0. So f prime is doing something like that. This is not very accurate. I'm just making a general sketch. And after x equals 3, f prime, the slopes are positive again and increasing. So f prime looks something like this. Now, in terms of f double prime, that's just the slopes of the graph of f prime. So we could treat f prime as the new f in some ways and apply the same treatment to find its derivative. So here we have only, it looks like one horizontal tangent line. So therefore that will correspond to the x-intercept of f double prime. To the left of 1, f prime is sort of decreasing, so it's got negative slope, so the slopes will be negative in that sense. And then after x equals 1, it seems like f prime is increasing, so its slopes will be positive, and it looks something like this. So again, these are not very precise, but it just gives you a general recap of how to sketch functions' derivatives. And the most important thing is this is a very strong correspondence between the behavior of f prime and f double prime. And when we understand the connections, then we will be able to be given graphs of f prime or f double prime and infer what f must look like. And that's what we will do next. Now let's review what in particular f prime tells us about the function f. So you will recall that if f prime is positive, this means that f is increasing, and we have a curve that looks like that. And you can see that the tangent line anywhere along that curve is positive in slope. And if f prime is less than 0, not surprisingly, it means that f is decreasing, and the function looks like that. And you can see that if you draw a tangent line anywhere there, the slope will be negative. All right, so the next 3 statements are really the first derivative test. It's just a review of the first derivative test, which tells us that, for example, if f prime is equal to 0 or dne, and f prime changes from positive to negative on either side of that, what's known as a critical value, then f has a local max there. And so what does that look like visually? Well, we see here, so f prime is positive to the left, and then 0 at that point there, and then negative, and obviously that means f has a local max right here. All right, and then now if f prime is 0 or dne and f prime changes from negative to positive, then that implies that f has a local min. Now, the dne is very important because we see here an example of where there is no, this is a corner, a cusp, there is no derivative right there, that does not exist. But notice that f prime changes from negative on this side to positive, and that would be a way to confirm that f has a local minimum. And then there's the situation where f prime equals 0 d and e at some point, called the critical value, and f prime does not change sign. Well, then we have this situation. So f prime here is 0, and f prime is positive on this side, and f prime is positive on the other side. And so we have this situation. Sometimes this is referred to as a saddle point. So let's call up that graph that we sketched the derivative of in the first slide. It's color-coded for a reason, as you will see shortly. So this is the solid line graph is that of f. And as we discovered before, we know that the graph of f prime begins like this. So I color-coded it in green because you will notice that the dotted line is above the x-axis, so that f prime is positive when the function is increasing. And in the orange section where the function is decreasing, right, so all along here, notice that the graph of f prime is below the x-axis. And it continues on like that. So let's summarize that. So an observation we can make is that f is increasing on negative infinity to negative 1 and also 3 to infinity. And not surprisingly, the graph of f prime is greater than 0 in both those regions. And you can see that the green dotted line is above the x-axis. So f we know is decreasing on negative 1, 3, and that corresponds to f prime being negative. And so now let's have a look at those red dots. What's happening at the red dot? We know that over here we have a horizontal tangent line, and it's also therefore a local max. But what does that look like how does that interpret in terms of the f prime graph? We see that the f prime graph changes from positive there to negative. So at x equals negative 1, f prime here is positive, and to the right of negative 1, f prime is negative. So that's what we look for on an f prime graph. Now look at the blue dots. So in the case of the blue dots, that corresponds to a local minimum there. So f prime is 0 there. But notice, so f has a local minimum at x equals 3. How does that correspond to the f prime graph? We see that f prime changes from negative to positive. So here f prime is negative, and here f prime is positive. So this is just giving us a visual connection between the graphs of f and f prime, kind of confirming what we know from the first derivative test and information about how f prime and f are connected. Now it's time to get the second derivative involved, sort of recalling what the second derivative tells us about the function f and about f prime while we're at it, because they are, all three of them, intimately connected, as we will see. So recall if f double prime is greater than 0, this is synonymous with f being concave up. It's a way to test for concavity, actually. And what does a concave up graph look like? Something like this. And sometimes I draw little sort of normal lines with arrows, and you see they're all sort of pointing upwards as I model the curvature. Now, the important thing is that the definition of concave up was, in fact, a situation where f prime is increasing as you move from left to right across the curve. So to visually see that, let's just draw some little tangent lines from left to right, and we will see if we give approximate values. This looks like -1, -0.5, 0, maybe 1, 2. We can see that the values of f prime are indeed increasing. And so it follows that if the second derivative is less than 0, that's a situation where f is concave down. And we have a situation like that. If I follow the curvature with little arrows, they are pointing downwards. And not surprisingly, it also follows that f prime is decreasing from left to right. Again, this is a little harder to see because you have to take into account that decreasing means becoming more negative. So say that slope is +0.5, then 0, and here the slope is -0.5, and here it's -1. You can see those values are becoming more negative. So here we have what happens when f double prime equals 0 or DNE and the f double prime changes sign. Well, obviously that means that we have a change in concavity, which means we have a point of inflection. So at a point of inflection, so here's a situation where here we have an inflection point here, and we can see that the concavity changes from down to up. And this is another situation where this is an inflection point. It's also a place where the tangent line is horizontal, and it is going from concave down to concave up. And a real key feature here is that in terms of f prime, if we see that f prime is changing from increasing to decreasing or vice versa, that's our indication that there is an inflection point on the graph of f. So I'm going to call up the graph of f and f prime from before, and now we're going to get f double prime into the picture. So remember that f double prime is the slope of f prime. So we see that for the green section of f prime, so all along here, we see that it's decreasing, f prime is decreasing, which means that f double prime is going to be negative. So here we have the beginnings of the graph of f double prime. The dotted line graph represents f double prime. So the green section, now let's focus in on the green sections of all three graphs because they're all connected. So f itself is concave down all the way up to x equals 1, which corresponds to f double prime being less than 0, under the x-axis in other words. And how does this correspond to f prime graph? Well, we see that f prime is decreasing, as we were discussing in the previous slide, all the way up to x equals 1. And then let's have a look. Let's continue it on the right side of x equals 1. We have that the function itself is concave up, which translates to f double prime being positive. So the orange dots are above the x-axis. And importantly, we see that f prime is increasing over that interval. So what's the important point here? The important point is at x equals 1, because we have a change of concavity, a lot going on all three graphs. So f has a point of inflection because the concavity changes, and we see that on the f double prime graph, we see that this is this point here. First of all, it's an x-intercept of the f double prime graph, and it corresponds to the point of inflection. But what's also important here is that, so f prime changes from decreasing to increasing. So I guess I'm going to put a little red point there. At x equals 1, we see that the f prime graph changes from decreasing to increasing, indicating a point of inflection. Notice also that f prime has a relative extrema here, because so this is an important connection. So the derivative of f prime is f double prime, and we see that at this point f double prime equals 0, which is why we have this x-intercept on the f double prime graph. So all these connections, probably good to take notes on this slide before we move on and start practicing. So for our first practice problem, we're going to look at a classic calculus problem where you're given a graph of f prime and you have to answer some questions about the function f, even though you can't actually see the function f. This graph is taken from free response exam on the AP/AB test, but the questions I've modified just to sort of for our purposes. So notice that you're asked to justify your responses. This is very common in calculus, so we actually set the framework up for here. So f is increasing, we know. Let's fill in the justification first, when f prime is greater than 0. And if you follow this laser pointer, where is f prime, the graph of f prime positive? Above the x-axis from -2 to -1, and then from 2 all the way up to 8. Now you might say at 6 it's actually 0, but we don't talk about a function being increasing at a point, only over an interval. So what is it doing on either side of 6? It's still increasing. So we would say it's increasing from -2 to -1, unified with 2 to 8. Next question, where does f have a relative max? We're looking for f prime changing from positive to negative. And so that seems to be happening only once around -1. At -1, f prime changes from positive to negative. So that is the location of a relative max. Where is f concave down? Now, again, because we don't have a graph of f double prime, we need this important fact that we are looking for where f prime is decreasing. And f prime is decreasing, it seems, from -2 to 0, and then also from x equals 4 to x equals 6. So we'll put that here, -2 to 0, unified with 4 to 6. And finally, where does f have an inflection point? So we are looking for f prime changing from increasing to decreasing, or vice versa. From increasing to decreasing, or vice versa. So where is that happening? Well, it seems that at x equals, let's see, 0, so f prime is decreasing and then increasing. At x equals 4, increasing then decreasing. And at x equals 6, f prime decreasing and then increasing. So we have 3 inflection points at x equals 0, 4, and 6. So for this problem, we are given a graph of f prime again, but this time we get to sketch the graph of f. So how to go about this? My advice is to always start by finding the x-intercepts of f prime, because these will correspond to horizontal tangent lines of f. So I see an x-intercept at -2, at 1, and at 4. And then let's investigate what's going on around, say, x equals -2. F prime is positive just before, negative after. That means that at x equals -2, f must have a local max. We don't know where that local max is located, how far up or down, but so there's some sort of flexibility here in where you place this. So I'm going to place it up here, a little local max, just to maximize the space I'm given. Okay, so in x equals 1, f prime is going from negative but remains negative on either side. So here we have a little saddle point, right? So it doesn't have to be perfect, just a little sketch so that we can connect the dots when we're ready. And at x equals 4, f prime is going from negative to positive, so we have a local min here. Okay, and those, let's call those points A, B, and C. So there are horizontal tangent lines on f. So now the next thing to look for is the relative extrema of f prime, because these will correspond to inflection points. So for example, at -1 is a local min, so f prime goes from decreasing to increasing, so we have an inflection point. And I'm going to put that, because I know I have to connect A to B and get through that inflection point, I'm going to put it there, call that M. And at x equals, oh, look, x equals 1. We also have a local max, so it turns out that B is an inflection point and also a location of a horizontal tangent line. And then we have a local min here, so we have another inflection point. I'm going to put it right about there. Let's call that N. At this stage, we can also check concavity in increasing and decreasing, but if you trust me with this, you actually can just connect the dots, and the concavity and all that increasing, decreasing will work out in the wash. So I'm coming through the max, local max here. I've got to get through that inflection point, so I better not change concavity until I get there, and then I get to change concavity. And B is also an inflection point, so it looks like concavity is changing there, but now I have to stay with the same concavity, and at N, the concavity changes, and it looks like the function is concave up after there. Now, how do we know that that's actually, how can we trust that that's true? Well, let's look at, let's just look at some features, make sure when the function is increasing. So for example, the function is increasing from -3 to -2, and we see that f prime is indeed positive in that area. Let's also look at when it's concave down. F is concave down from -3 all the way to -1 according to my sketch. And that corresponds to the interval over which f prime is decreasing. So you can go through and keep checking the features, but I promise you, by connecting the dots in the way we did, we actually made an accurate graph of f. For our third and last practice problem, we're given the graphs of f, f prime, and f double prime, and you have to determine which is which. So there's an obvious go-to with these type of problems is to look for max and mins on different functions and make sure that the derivative graph would have that max or min as a x-intercept. So let's just start with the blue one. And we see that there is a min right here, somewhere between 0 and 1. So that means that the derivative of this graph must have an x-intercept there, which it looks like the green graph does. Now let's make sure I'm pretty sure that must be it, but let's check other features. For example, feels like the green graph is the derivative of the blue one. Well, let's confirm. And we can see that to the left of x equals 0, the blue graph is increasing, and we can see that correspondingly the derivatives are all positive here. After, on the right side of x equals 0, this graph is decreasing, and we can see that this graph, the green graph, is below the x-axis, is negative. So pretty confident that the green graph is the derivative of the blue graph. Notice that there is an asymptote on the blue graph at x equals 0, and that shows up in the green graph as well, because the blue graph is undefined at x equals 0, so its derivative would be undefined. Now let's go to the red graph, because we see here, so let's change that, here we go, that we have a local min right there, which means that somewhere between -2 and -1 there should be an x-intercept, and we see that right here on the blue graph. And now also another interesting feature is that we see that there's a vertical tangent line at x equals 0. So even though the function is continuous, notice that it's not differentiable at x equals 0. And that's why we have an asymptote in the blue graph. So we can see that the blue graph is the derivative of the red graph. So putting them in order, it appears that this must be f, the red graph, the blue graph must be f prime, and the green graph f double prime.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.